So we are discussing the microsensors and microtransducers. So we had already discussed about the gyroscope accelerometers, the mechanical switches, the MEMS based switches in detail, a flow transducers. Now we will discuss about the haptic interface and the sensor skin for robotic system. So as far as these haptic interface are concerned, this haptic sensor detects the touch, force and vibration while also providing a tactile feedback such as vibrations or force to simulate the sense of touch. The haptic interface that provides a continuous sensation which allows the human to interact with the computer system and other types of machines through the sensation of touch, enabling a person-machine communication. So it's a kind of man-machine interface which can be specifically established using this haptic interface. So unlike a traditional interface, it provides a visual and auditory information. The haptic interface generates a mechanical signal that simulate human kinesthetic and touch channel. The haptic interfaces can be used to add sensation of touch to virtual and augmented reality experiences. So ideally, the haptic system should be capable enough is in getting interfaced with the processor, the driver, the actuator and the vibration sensor. Now, let us see some of the real life example of these haptic devices like smartphones and tablets. So the haptic feedback in touch screens like Apple Haptic Touch, Android vibration alerts, etc. are some of the examples of haptics. With reference to smartwatch and wearables, vibration for notification, fitness tracking feedback are some of the examples. With reference to laptop and keyboard, these haptic enabled trackpads are efficiently used. And on the gaming controller perspective point of view, force feedback in PlayStations and DualSense and Xbox controllers are used. On haptic VR gloves perspective point of view, it allows the users to feel the virtual object, example this haptic gloves, etc. Now, with reference to robotic surgery and telemedicine, so a Da Vinci surgical system provides a force feedback to the surgeons to appropriately incorporate the system. And haptic steering wheel arrangement is concerned, a vibration alert drivers to the lane departures is one of the practical application of these haptic steering wheel based system. Touch screen controls which has a haptic feedback in infotainment systems for safer driving, haptic pedals and seats, a vibration in a seat for safety warning, a remote operation of robots, haptic feedback enhances the control of robotic arm in hazardous environment, aerospace flight simulators, a force feedback in a pilot training are some of the examples of these real life examples of haptics. Now, when we try to in order to closely understand the haptic system, so we need to have exposure to the components of haptic interface like sensors for haptic interface. It detects the user's input and interaction with the environment. It also measures the force exerted by the user on the interface. So with reference to actuator perspective point of view, it generates a physical feedback like forces, vibration or movements. With reference to control system perspective point of view, it processes information from sensors, it manages a feedback generation through the actuator and it implements an algorithm to create a realistic haptic sensation. A software perspective point of view, a mathematical model of haptic feedback, algorithm for haptic rendering, synchronization of haptic and visual feedback. As far as electronic component perspective point of view, it has a control sensor and actuators and a process signal and a process signal to manage the power. As far as the types of sensors used for haptic interface is concerned, haptic interface uses various types of sensors to detect the user input and interaction, which includes the force pressure sensor, that is a piezoresistive sensor or a piezoelectric sensor, a capacitive sensor and a triboelectric sensor. So these sensors detect contact conditions, pressure values and force distribution when a user interacts with the haptic interface. With reference to temperature sensor perspective point of view, there is a pyroelectric sensor. So as far as these pyroelectric sensors are concerned, it used to detect the temperature change and it provides the thermal feedback. With reference to tactile sensor perspective point of view, a sensor mimicking human mechanoreceptors like Merkel cells, Ruffin corpuscles, Meissner corpuscles and Pezzinin corpuscles are some of the human mechanoreceptors corpuscles which are being established. So these sensors detects the various tactile stimuli like pressure and vibration in these textures. Now let us discuss about the actuators used in a haptic interface. These actuators are used in various combinations depending on the specific requirements of the haptic interface, such as precision, power consumption, form factor and the desired tactile effects. Like let us take an example of an eccentric rotating mass motors. So it consists of a balanced weight attached to a motor shaft. It rotates, the rotation creates a kind of a vibration and it is commonly used in mobile devices. So this is a kind of a rotation motor eccentric mass. With linear resonant actuator is concerned, it uses a magnetic mass which is attached to a spring. It produces more precise and a controllable vibration. It is often used for high-end smartphone and controllers. So with reference to linear resonant actuator perspective point of view, it has a spring, a mass, a magnet and a coil assembly. A mass with a spring and a magnet which is available over here and which is mainly meant for the appropriate deflection studies. These, when we try to consider these actuators are used in haptic interface like piezoelectric actuators. These piezoelectric actuators use material that deform when electrical current is applied. It provides a high frequency and a localized feedback. It is also used in advanced touchscreen as well as precision related applications. With reference to electroactive polymer perspective point of view, it changes its shapes or size when simulated by an electric field. It can create more complex and textured sensations. It is still in the development of it is more in the development of a kind of a commercial applications. When we try to talk about this feedback in an haptic interface, these haptic feedback can offer more interactive means and it mimics the feeling when an event occurs naturally to enhance the effect of a virtual reality and thereby advancing the user experience. The haptic feedback in human machine interaction HMI now includes a vibration and an electrical feedback which can not only transmit the contextual informations but also provide a people with a clear, accurate and less interfering informations. Now as far as this feedback in haptic interface is concerned, so it has a kind of a kinesthetic feedback. These kinesthetic feedbacks are nothing but it simulates weight, pressure and force through muscles, tendons and joints. It is used in force feedback device like joystick and VR controllers. It also provides a sense of resistance or movement. When we try to talk about the tactile feedback, it simulates the sense of touch on the skin surface. It includes several subtypes like vibrotactile. These vibrotactile uses vibration to simulate textures and it also provides alerts. As far as electrotactile is concerned, it uses electrical impulses to simulate nerve ending in the skin. As far as ultrasonic tactile is concerned, it creates a mid-air tactile sensation using focused ultrasound waves and a thermal feedback which simulates a kind of a temperature change. When we try to talk about the force feedback, it applies forces to resist or assist user movement. It is used in gaming controllers and virtual reality system. It enhances the realism by simulating a physical interaction. As far as textured feedbacks is concerned, it provides a detailed information about the surface properties. It can be achieved through a spatial tactile feedback or a vibrotactile patterns. As far as electromagnetic feedback is concerned, it uses a magnetic field to create a kind of a tactile sensation. It is less common but used in specialized applications like haptic feedback suits, etc. So, which is more on the wearable side. Now, let us discuss about this kinesthetic feedback in haptic interface. These kinesthetic feedback, it provides users with a sense of movement, position and force through the muscles, tendons and the joints. To simulate this physical property of the object, so ideally we need to have different parameters like the size, density and the resistance. For example, in the case of a video game character, a character uses a heavy vehicle might require more force to move, providing a realistic sense of weight and resistance. With reference to micro robotic perspective point of view, there are such kind of kinetic feedback based haptic interface which are used for controlling the movement of the drones, micro drones, so appropriately these drones can move within a particular domain and the orientation of the drone can be changed through this haptic interface. When we try to classify this kinesthetic feedback, the kinesthetic feedbacks are classified into two. One is called as passive kinesthetic and another one is called as active kinesthetic. So, these type of feedback only impedes the user movement by providing resistance. It is based on the physical attributes of objects such as textures, weight and rigidity. So, this kind of passive kinesthetic is commonly used in robotic surgery, where surgeons sense the resistance and pressure during operation, enhancing the precision and the realism. In the case of active kinesthetic, so this type of feedback can both impede and assist the user movement. It actively applies force to guide or support the user's action, simulating the interaction with the virtual object. It is like some of the examples which is found in VR gloves, haptics exoskeleton and specialized gaming devices. It enhances the immersion and realism by simulating the physical properties of the object in the environment. Now, when we try to talk about the tactile feedback, it refers to the physical sensations experienced when interacting with the surface or device providing the information. So, some of the key aspects include textures, vibration, pressures, etc. So, as far as these types of tactile feedback is concerned, we have the spatial type tactile feedback and a non-spatial type tactile feedback. So, in the case of a spatial type, we have the surface friction, the skin indent and the electrosimulation. So, like in these particular cases, it offers more detailed information about the edges and the shapes, and contact spatial haptic utilizes mechanical technologies like friction, surfaces and skin indentation deformation. The electrical simulations, while the latter stimulates nerve ending to trick the user brain into the feeling contact. As far as the non-spatial vibration is concerned, it provides a sense of texture and cues through the vibration patterns. Now, let us talk about the control system in haptic interface. There are two popular control methods which are widely used in haptic controller design. One is called as the impedance control. The operator motion input is measured and the reaction force is fed back to the operator. Next is called as the admittance control. So, as far as in this admittance control is concerned, the force exerted by the operator are measured, positions are fed back to the operator. Both impedance and the admittance control are also two basic methods for interacting with the virtual environment. Like either it might be a human machine interaction or it might be a human robot interaction. Now, let us discuss about the sensory skin for robotic system. So, as far as this sensory skin is concerned, it is a recent advancement in soft robotics which has led to the development of skin inspired sensory system that closely mimics the functionality of a human skin and muscles. These innovative robots integrated electronic skin, which we call it as a e-skin, with artificial muscles. It enables them to sense their environment and adapt their environment in the real time. When we try to closely observe the sensing capabilities of e-skin, so we have a pressure which detects the normal forces applied to the surface, a strain which measures the deformation and the stretching, a shear which senses the lateral force and the friction, temperature which monitors the thermal changes, humidity which detects the moisture level in the systems. As far as UV is concerned, it measures the ultraviolet radiation exposure. Proximity perspective point of view, it detects the nearby object without any contact. And a vibration sense and vibration perspective point of view, it senses a high frequency mechanical oscillation in these particular systems. Now, when we try to look into the overall sensing mechanism, this e-skin utilizes various transduction method to convert a physical stimuli into a measurable electrical signal. So, this measurable electrical signal can be in the form of a resistive type, it might be in the form of a capacitive type, it might be kind of a piezoelectric type, it might be a kind of a triboelectric type, it can be in the form of a thermal type, and it can be for a iontronics type, which is a kind of a high resolution slip sensing which is being employed. Now, in addition to this, when we try to talk about the robotic sensing, so we have the vision sensing. Some of the components of vision sensing includes the lighting, the lenses, the image sensors, the vision processing, communications and data collections. With reference to functionality perspective point of view, it allows the robot to perceive its environment and gather the information about it. With reference to sensor perspective point of view, it has an orthographic projection and a perspective projection. And an application perspective point of view, it focuses on the navigation and localization of the system. Now, when we talk about the robotic sensing, the hearing sense also considered to be one of the key parameter for a robotic sensing. So, in this particular case, we have the microphones and other sound sensors, we have the amplifiers in place, we have the analog to the digital converters which participate in this particular robotic sensing, a computer system, algorithm and software and a data collection will also participate in this. As far as functionality perspective point of view, a perceives sound in its environment and it gathers the information about them. As far as sensor type is concerned, it has a sound sensor, a piezoelectric sensor, ultrasonic sensor and infrared sensors are different types of sensors which are being used. On an application perspective point of view, it has a sound localization and tracking, sound classification and noise cancellation are considered to be some of the applications. Now, with reference to robotic sensing, we have the tactile sense where a sensing, data collection, data processing, decision making and actuation plays a vital role. With reference to the sensing, we have a perceive physical contact and gather informations. And there are different types of sensors there which includes the pressure sensor, temperature sensors, force sensors and strain sensors and tactile array of sensors which are considered to be some of the robotic sensing systems. And then as far as some of the key applications are concerned, it includes the object identification, the force feedback and the surface sensing which contributes towards the tactile sensing. Now, we can also consider the electrical nose. So, in the case of the electrical nose, some of the components of sensing includes the sensors, the data acquisition system, the data analyze system, a sample introduction system, power supply and housing. It detects and identifies the different chemical compounds. So, if we closely observe the sensor, so some of the sensors includes the metal oxide semiconductor sensor, the quartz crystal microbalance sensor, the surface acoustic wave sensor, a gas sensor where there is a solid state gas sensor and an infrared gas sensor, a catalytic gas sensor and an electrochemical gas sensor, and some of the nanowire gas sensors are also used for participating this electrical nose. Then we have the mass spectrometry sensor which also participates. Now, with reference to application perspective point of view, we have the chemical analysis, odor tracking, and the environmental monitoring which exhibits. Now, let us talk about the electronic tongue, so which is used as a kind of a robotic sensing. So, in the case of an electronic tongue, there are wide varieties of groups which works on the conductive polymers, ion selective electrodes, optical fibers, surface acoustic wave devices, and data collections. So, the main functionality includes the detects and identify. It is mainly meant for detecting and identifying the different chemical compounds. So, some of the key aspects which includes the pH sensor, the conductivity sensor, the temperature sensor, the chromatography sensor, electrochemical sensor, and a spectroscopic sensor. So, application perspective point of view, it is used for a chemical analysis and a flavor detection. On a sixth sense perspective point of view, we have the sensors, the manipulators, the processors, the power supply. It has an housing with an enclosure, a communication system, a machine learning system, and a data collection system. So, this allows the robot to perceive its environment and interact with it in various ways. So, like there are different types of sensors are there. One is a kind of a kind of a temperature sensors, a pressure sensor which contributes to it, a humidity sensors, and a cameras which also contribute to the overall processing of the systems. The microphones and the LiDAR sensors will also gets integrated for this sixth sense. With reference to the overall perspective, it is viewing, mapping, creating a multimedia reading experience. It is for making calls and interacting with the physical object. So, this is a kind of a tactile sensor in the first robot, like which is meant for which has a tactile LED back and a LED head sensor. This is located on the robotic head, and this sensor is likely designed to detect a touch or the proximity. So, it can be used for a kind of an interaction and allowing the robot to respond in the physical contact gesture. And then there is a stereo microphone is there, which is positioned near the head area. The stereo microphone enables the robot to capture the sound in high fidelity. These features likely support the voice recognition and the audio command or environmental sound reductions. With reference to face detection, there is a illumined face LED panel. This panel appears to serve as a display on the robot's face. It might be used to express the emotions, provides a visual feedback, and to communicate information in the case of through dynamic LED patterns. So, distance sensors are deployed, which is located at the front of the robot. This sensor helps to measure the distance from object or obstacles. It is likely used to for navigation, collision avoidance, or spatial awareness. And there is a tactile LED back sensor which is situated on the back of the robot. This tactile sensor detects touch inputs on its rear side. It might support the interactive features or it provides feedback when touched. And there is a pause button sensor is there, a physical button located on the body of the robot, possibly used to pause its operation or put it in a standby mode. So, these are some kind of commercially available sensors which are being established for different applications related to this tactile and related monitoring. Now, let us discuss about a new concept called machine skin. So, as far as this machine skin is concerned, this is a kind of a customized smart material based flexible sensor which can be integrated in any kind of legacy based structures. So, this is mainly meant for kind of a macro level systems. However, using a certain amount of flexible triboelectric generators, it can also be integrated in the simple micro level system. So, when we try to consider this machine skin, so let me just give you a simple example. Like there is a lathe. So, we need to have a condition monitoring of the lathe. So, this is a pretty old lathe where instead of considering, so in this particular lathe, some of the key parameters which are involved are the temperature sensor, or the temperature which is getting generated because of the spindle rotation, a vibration because of the undulation in the structure, a flow because of the movement of the flow in the liquid, and then a kind of a strain which established over here. Now all these sensors should be on a micron level, and all these sensors should be on a customized base system. So a kind of a customized structures can be deployed by integrating smart materials, or by designing the smart materials to sense these particular parameters. So like for example, in the case of a temperature sensor, we can use a customized shape memory alloy structure. In the case of a vibration sensor, we can use a customized triboelectric nanogenerator. In the case of a micro strain measurements, we can use the SMA based strain gauges. Then in the case of a flow measurement, we can use an optical fiber based sensors. We can also use a pseudoelastic SMA for vibration damping, etc. Now whatever sensor data which is being connected, so these sensor data can be used, so these systems can be modeled in the form of a digital twin, so that all the sensory data can be captured and it can be monitored through this digital twin. So what happens is, this digital twin will continuously interact with these with the machine, and it will try to capture the data, and it can be used for prognostic related application. The concept of machine skin is proposed to cater to this issue. It consists of an array of an IoT enabled sensor strategically positioned on the surface of a machine to collect data on numerous parameters such as temperature, variation, flow rate and strain. So the collected data will be subsequently processed and analyzed for a prognostic purpose, and the result will be displayed on the dashboard via a server based system, resulting in creation of a digital twin depicting the entire machine and allowing the operator to visualize and understand the prognostic data in a user friendly manner. So some of the key advantage of this machine skin process is, like for any kind of legacy machine or any kind of machine which requires a customized sensing, such kind of machine skins can be deployed. Second important advantage on which the machine skin are focused are, like these are some kind of self-energized system, so that it does not require an external power. Third important point is, the whatever energy which is being generated by these triboelectric nano generators can be efficiently used to power up the IoT module, so that it acts as a kind of a plug and play module, and from the plug and play module the digital tools will start working and it will start interacting. So this machine skin is completely new, and it is being taken up to the next level for different application. Next, this is a kind of a case study. So in this case study, it's a kind of a gesture based SMA actuated robotic hand for human machine interaction. So like currently we are talking more on the industry 4.0 related applications. However, there is a need to move towards the industry 5.0 application, which is more towards man-machine interface. So as far as in this man-machine interface is concerned, the sensory system what has been deployed should be capable enough in interacting with the main system, so that appropriately it can be used for a seamless communication, and then a kind of a seamless transformation can happen. So in this particular process, there is a need to go for a gesture recognition system, and then this gesture recognition system should be appropriately capable enough to interact with the microcontrollers, the relays, the SMA robotic hand and the power source. Now the main motto of this particular process is like it is a glove which is integrated with a flux sensor, which is used for gesture recognition. However, on the other hand, there is a kind of a 3D printed hand with a SMA based robotic structures, with the SMA based actuators. So when these gesture gloves are being appropriately moved, appropriately these robotic hand also gets actuated, and like there is a relay circuit which is being deployed, which will have a control over the position and orientation of this SMA based robotic hand. So if you see in this, so this is a kind of a demonstration and training which is being deployed for the gesture control, that is the glove which is integrated with the flux sensor, and the gesture recognition involves a kind of a control signal where different gestures are recorded. So either it might be a 1 finger movement, 2 finger movement or a 5 finger movement. Appropriately, these signals are translated to the movement. Like for example, so in this particular case, so this is a kind of a gesture which is shown, and the distance between the man and the machine is close to around 8 meters. So appropriately when the gesture movement, so there the movements are translated in handling the system. So this is a simple technology, like the thought process of this technology is a kind of a remotely operated bomb diffusion system. So this is a kind of a wire cutter which is being placed over here, and this is operated using a kind of a man-machine interface, that is a kind of a gesture control moving on the robotic system. Now there are different kinds of high resolution electronic skins are also used for such kind of applications. So one of these, which includes a robotic sensory skin. So as far as in this particular case, instead of a flexoelectric or a shape memory alloy structures, a kind of piezoelectric sensors are being deployed. So in these piezoelectric structures, a robotic sensory system of a large area high resolution electronic skin for robots are being embedded. So the research focus on creating a flexible and a sensitive e-skin that can enhance the robot ability to interact with their environment and perform a complex task. So the e-skin uses a piezoresistive sensing mechanism. The e-skin covers a large area from close to around 70 centimeter to 50 centimeter with the high resolution sensing units, close to around 5806 sensing units. And the e-skin can detect a pressure as low as 28 Pascal. So it has a fast response time of 30 milliseconds. It allows for a real-time sensing, and the e-skill can be successfully integrated with the robotic arm. So the main advantage of such kind of high-resolution electronic skin is it can achieve a real-time tactile sensing and grasping control of the robotic hand. And by considering the hardness and surface roughness and brittleness of the object to be grasped, and it is also used for comparing the real-time pressure distribution on the robotic hand with a preset. It decides when to stop grasping and when on lifting the object and grasp this object, such as delicate components like papers, balloons, etc., without damaging them. In fact, it is also in the case of a silk industries, these are being used for grasping it appropriately for silkworms, etc. The system simulates the tactile and the motion feedback process of the human skin, nerves and muscles, and can be directly attached to the surface of the existing intelligent machinery. It offers an advantage of compactness and easy installation without forcing any major changes to the mechanical structures. So these are some of the kind of a high resolution electronic skin based systems which are being deployed for a robotic application. So just to summarize, so the main objective of this particular module is to understand the impact of the microsensors and the microtransducers. Like it's a kind of a high level, more focusing on the acquisition and manipulation related systems. Okay, so the content comprises of gyroscopic accelerometers, the mechanical switches, the flow transducers, the haptic interface, and the sensory skin for robotic system. So we had discussed about the overall classification of a gyroscope. So some of the key aspects of the gyroscope, including the vibrating structures. Then we are trying to study the classification of this vibrating structure gyroscope, including the ring gyroscope, a tuning fork gyroscope, a hemispherical resonator gyroscope, a dynamically tuned gyroscopes. Then we have also discussed about the optical microscope based gyroscope accelerometers, which includes a fiber optic gyroscope and a ring laser gyroscope, which doesn't require any kind of mechanical structures. Then we had a discussion on micromechanical switches, about the overall configuration of these micromechanical switches, the basic working principle of these micromechanical switches, which includes the magnetic field and an LED field, and the membrane switches and the snap action which exist. Then we had some discussion about these MEMS based switches. In the case of MEMS based switches, we had discussed about the different configuration, including the electrostatic switches and the electromagnetic switches, electrothermal switches and the shape memory alloy switches. So some of the key parameters which are involved in fabricating, in designing and fabricating such kind of switches, which includes the switching time, the transmission performance, the contact resistance. So we had also discussed about the reliability characteristics of it, the overall application of such kind of MEMS based switches, and then the major key challenges and the advantages which are involved. Some of the recent advances of these switches, which includes a micro power Hall effect switch, a multi-material MEMS based switch, a self-enhancing piezoelectric actuators, a soft electromagnetic actuators, and a polymer based electromagnetic actuators. Some of the future trends which are involved, like AI integration for predictive maintenance, self-healing contacts, energy harvesting applications, biodegradable switch technologies, and enhanced integration with IoT and smart systems. So we also had a discussion about the flow transducer, different configurations of the flow transducer, key components of the flow transducer, some of the features, energy conversion mechanism, measurements method, and then signal processing, and the overall other roles of these flow transducers and micro robotic systems. And we also had a discussion about the different types of flow transducers, including the thermotransfer methods, then the time of flight methods, thermal time of flight methods, then the ultrasonic methods, and we also had a discussion about this magnetic inductive principles, vortex principles, and then Coriolis flow sensors in detail. So a new concept on triboelectric nanogenerator based flow sensors has been discussed, and the demonstration of the same has been demonstrated over here. Then we had an interaction about this haptic interface, the overall application of this haptic interface, the components involved in the haptic interface, sensors used in haptic interface, the actuators used in haptic interface, the feedbacks in haptic interface, and the overall kind of, so the classification of this haptic interface can be classified with reference to the kinesthetic feedback and the tactile feedback, the overall control systems involved in these haptic interface. We also had a discussion about this sensory skin for robotic systems, the various types of robotic sensing which are being established, including the vision, hearing sense, tactile sense, electrical nose, electronic tongue, and sixth sense. We also had a discussion about the tactile sensor for a robot, for a commercially available robot, how the tactile sensors are being employed. So there is a concept of machine skin which is coming up in a bigger way. So the machine skin has a potential application towards the man-machine interface and the man-robot interface. So one case study on machine skin has been demonstrated over here. A gesture-controlled robotic system for controlling the robot even at the remote location. This is a kind of a demo which was demonstrated to show how the gesture control works, and even at a 8-meter distance, and how it is being controlled and how it is being monitored. High resolution electronic skin for micro robots, and how these high resolution skins are employed for robotic related application. These are the references which have been used for this particular lecture.